Hey P Chemistry, welcome back to another video. Today we're talking about Unit 7, Equilibrium. Alright, this unit is a unit that many people normally struggle with because of what we call ice tables, which we'll get to. But the concept itself is not too difficult. Alright, so some vocabulary to start with. We're going to talk about equilibrium, Le Chatelier's principle, the equilibrium constant expression, and reaction quotient. Alright, if you are in advanced chemistry, you've talked about Le Chatelier principle before, but the rest of this, I believe, would be new to you. Okay, so often in chemistry, we do lie to you. I'm so sorry. But we lie to you to make concepts simple, because chemistry concepts are quite complex that if we just tell you the truth from the beginning, it will not make sense. Right? So we lie to you a little in the beginning to make it simple. Then as we go along, we reveal some of the small truths. This is one of them. So many reactions do not go to completion, right? We've talked about that a little bit before, but it's not always going to be just an arrow, it's gone and done. What we normally have is an equilibrium. So what equilibrium means is that the rates of the forward and reverse reaction are equal. Not the concentrations, the rates, okay? So that means the rate that H2O liquid here is turning into gas is equal to the rate that the gas is turning into liquid. All right. So with equilibrium, right, this image here also shows to the right. The top graph shows that the rate, so remember if you see here, the blue one is going to be the reverse. The red is the forward, and by forward and reverse, we just mean which direction we're going. If it's forward, we're reading from left to right. Reverse, we're reading from right to left. So as a reverse, our products are going to be the reactants. Okay, so our reverse rate and our forward rate are going to equalize. They're going to be the same. But the concentrations, the amount of each we have, is still going to be different. Okay. During an equilibrium, if we have something called a stress, we can shift it. We can move it around a little bit. Okay, so this will either favor the forward reaction, which is going to the products, or it'll favor the reverse reaction, meaning we'll make more reactants. Okay, and with these stresses, think of it like a balance, right? If you have a balance, you have it equal on both sides, and then you remove a part of it, it's going to shift, right? The right side, if we remove C, the right side goes up, the left side goes down. So what do we need to do to make it equal again? That's what we're going to figure out. That's what we're going to figure out what happens. Okay. So with Le Chatelier principle, there's a few different shifts we can have. We can have shifts in concentration. Okay. So if we increase the reactants, if we have more things on the left, we want to get rid of them. So it'll shift to the right. Okay, so if we have an increase in reactants, we're going to shift to the right. It doesn't matter if it's both reactants, or we can also just have an increase in one. Okay. If we have an increase in products, the other side, it'll shift to the left. Okay. If we have a decrease, okay, so be careful with the wording, a decrease in reactants. So if we get rid of A, we want to make more of it. So it's going to shift to A, right? For the decrease, think of it like if you have a hole there, how do you fill the hole? You need to shift towards it, right? And then decrease in product, if we get rid of D, we'll need to make more of it. It goes to the products. All right. For pressure is similar, but this is going to be only for gases. Okay. So with pressure, we're going to think about it also with volume and moles. Okay. So let me make it an example. If we have H2O gas in equilibrium with H2 gas and O2 gas, so we'll need a 2 there and a 2 there. Okay. So if we increase the pressure, right, if we make the container smaller, we're going to shift to the side with less moles. So by moles, what we mean is our coefficients of the gases, right? So on the left, we have 2 moles. On the right, we have 3 moles because we have 2 H2s and 1 O2. So if we increase the pressure, we're going to go to the side with less moles. If we decrease the pressure, it's going to be the opposite. We go to the side with more moles because there's more space now. Okay, so you can think about it with volume also, right? If we increase the volume, so if we increase the volume, that would mean we decrease the pressure. And if we decrease the pressure, we go to the side with more moles. Okay, so you can talk about this with either volume or pressure, but it's only with gases. All right, with energy or heat, okay, so this is where thermodynamics kind of connects in. If we have an endothermic reaction, remember we said endothermic, the reactant, or sorry, endothermic, the heat is a reactant. Okay, this is going to act the same way as we did with concentration. If we increase the heat, so if we increase the reactant, it's going to shift to the right, to the products, to get rid of it. If we decrease the heat, decrease the reactants, we're going to shift to the left. Okay, so it works the same way as concentration. For exothermic, remember we said exothermic means that heat is a product. So if we increase the product, it's going to go to the reactants. If we decrease the product, it's going to go to the products. All right. And then some non-stressors. Catalysts do not change equilibrium because we're not changing the rate. We're just changing the activation energy. Okay. And inert elements, so the noble gases, right? Helium, neon, argon, krypton, etc. Those also do not change equilibrium because they don't react, right? They're noble gases. Inert. Inert means non-reactive. That's a good word to know. Okay, so if I throw in some helium into a reaction, nothing's going to happen. Okay, so remember with reactions, we have net ionic equations, so we can also do this with ions. All right, so let's look at these questions here. If we have this reaction, and A says, what would be the effect of adding NaF? So NaF is Na plus and F minus. That F minus is right there. We're adding more of our product. If we add more products, it's going to go to the reactants. Okay. So then look at B. B says HCl. Okay, HCl is H plus and Cl minus. Well, that Cl minus, not Cl minus. The H plus is right there. It's a product as well. So if we increase the products, we're going to reactants, the same effect. All right, and then C is what is the effect of adding helium. Well, helium is a noble gas, so there's no change, no effect. Okay, so anytime we're dissociating our ions, we call that the common ion effect with equilibrium. Okay, so with equilibrium, with a reaction, we can write an equilibrium constant, and all this equilibrium constant does is it compares our products to our reactants. It gives us a ratio. Okay, so our equilibrium product or equilibrium constant is shown here. We could do it for concentration or for pressure. Okay, it looks different, but it tells you the same thing. For concentration, it's the concentration of your products divided by the concentration of your reactants. And notice that your coefficients become the exponents. All right. It's the same thing for pressure. You're still doing products divided by reactants, and the coefficients are still your exponents. Okay. The reason we notate it differently is, remember the bracket symbol. That's for concentration. Okay, so brackets are for concentration. The capital P with something below is for pressure with a superscript. Okay, that's the only reason it's denoted differently. Otherwise, it means the same thing. It's a ratio of our product to our reactants. All right. With equilibrium constants, though, one thing to know: we do not include solids or liquids. Okay, so you're only including gases, aqueous. Yeah, just those two. Okay, so do not include solids or liquids. So if you have H2O liquid, don't include it. We don't care about it. Right, and then this bottom part here is just a note. There's a lot of different equilibrium constants, right? We can have KEQ. The EQ just stands for equilibrium. Kc is just the concentration constant. Kp is the pressure constant. Ksp, we'll talk about here in a minute, is the dissolution constant. Ka is for acids. Kb is for bases. These two we'll talk about next unit. All right. So there's a lot of different ways to write the equilibrium constant. They all mean the same thing, though. There's still a ratio of our products to our reactants. So anytime you see that capital K with something underneath it, it's an equilibrium constant. You're doing your products divided by our reactants. Okay? So don't let the 10 different ways we can show it mess you up. They mean the same thing. Okay? And since our K expression, our equilibrium constant, is a ratio of our products divided by reactants, if it's greater than 1, that means we have more products because the numerator is top heavy, right? So that means it's product favored. We have more products than we have reactants. If it's less than 1, that means it's denominator favored. Denominator favored, right? The reactants are favored there. Okay, so that's what the equilibrium constant means, just the products divided by reactants. Okay, so let's try writing them. So for these two up here, we're writing the concentration equilibrium constant. For the ones on the bottom, we're writing the pressure one. Okay, so for A, on this top one, so our Kc, our equilibrium constant for concentration, is equal to, remember we're doing our products divided by reactants. Okay, so our product is the HI, and it's a gas. But we're doing concentration, so I'm going to put the brackets, HI. And then remember the coefficient, the number in front, is going to be my exponent. So HI squared divided by my reactants are H2 and I2. And they each have a coefficient of 1. Okay. For B, our Kc, so for our products, we have NaNO3, we have CO2, and we have H2O. We have a liquid here. We're not going to include that. So we're going to do the same thing, but we just skip over the H2O. So we have a concentration of our products, our NaNO3 squared. Our CO2 does not have a coefficient, just 1, divided by our reactants. So our reactants are Na2CO3 and HNO3, and that HNO3 is squared. Okay, so that's for the concentration coefficient, the equilibrium constant for concentration, right? It's just the product divided by reactants. Your coefficients are your exponents. All right, so coming down here to the pressure ones, we're going to do the same thing. But instead of doing Kc, it's Kp. And then instead of doing the brackets, we're going to do the pressure with something as subscript. Okay, so for A, we have our Kp is equal to our products. So we have the pressure of NH3, and this is squared, okay, divided by our pressure of N2 times our pressure of H2, and H2 has a coefficient of 3, so that's cubed. All right, and that's it for that one. And then for B, we have our Kp is our pressure of a product, so we have pressure of NO squared, pressure of Cl2, coefficient of 1, divided by our pressure of NoCl, and that is squared. Okay, so this part should be pretty simple. Just products divided by reactants, the coefficient is the exponent. And remember, this is the same thing for any of those equilibrium constants. Products divided by reactants, coefficient is the exponent, don't include liquids or solids. Okay, and something that I want to mention, if you forget the format for Kc or Kp, if you forget how to write it, the notation, those are on your formula sheet. Okay, so if you forget how to write it, just look there and that'll help you. I think it's the first two in the equilibrium section. Okay, so let's do a couple examples where we actually solve for Kc, or we use Kc to solve for a concentration. Okay, so for A, we have a 3-liter flask, contains 2.4 moles of Cl2, 1 mole of NaCl, and 4.5 times 10 to the negative 3 moles of NO. Write the equilibrium constant expression. So we're going to write the constant expression, and we're going to solve for the equilibrium constant. We're going to do two things. Let me put that in a different color. All right, so we have two things we need to do here. But first, we're doing equilibrium constant expression. We're doing concentrations. We have moles. We need to find this in concentrations. So remember the equation for molarity. To find it, that's what we did. Molarity is moles divided by liters. Okay, so for Cl2, we have 2.4 divided by 3. That gives us 0.8. For NaCl, 1 divided by 3 is 0.33 molar. And then for NO, we have 4.5 times 10 to the negative 3 divided by 3. That's 0.0015 molar. Okay, so our equilibrium constant expression, our Kc, is products divided by reactants. Okay, these are all gases. We're going to include all of them. So we have our products first. So our first product is NO, that's squared. Second product is Cl2. Divided by reactants, we have NoCl, and that is squared. Okay, so that's our equilibrium constant expression. Now to solve for it, we're going to plug things in. So our NO, we said had a concentration of 0.0015, and this term was squared. Our Cl2 is 0.8, divided by our NoCl is 0.33, and that was squared. Okay, so if we plug this into our calculator, 0.0015 squared times 0.8 divided by 0.33 squared, we get 1.65 times 10 to the negative 5. Okay, and that's that. That's all you're doing. You're just writing the equilibrium constant expression, plugging your numbers in to find what Kc equals. Okay. For B, I'm going to set it up with you, but I want you to finish it the rest of the way. Okay, so we have the dissociation of acetic acid has an equilibrium constant of 1.8 times 10 to the negative 5 at 25 degrees Celsius. If the concentration of CH3COOH is 0.46 moles and 0.5 liters of water, and the anion, CH3COO minus, is 8.3 times 10 to the negative 3 moles and 0.5 liters, calculate H plus. That's what we get. Okay, so we're calculating the concentration of our H plus. All right, so start with setting up the equilibrium equation. We have our Kc, our product, so our H plus, CH3COO minus, divided by our reactant, our CH3COOH. Let me fix this H plus real quick. Okay, so that's our equilibrium constant equation. And what we need here is we need our concentrations. Okay, so we have our Kc. Our Kc is 1.8 times 10 to the negative 5. Our H plus, we don't know that. for CH3COO minus, that's our 1.8 times 10 to the negative 3 times and 0.5 liters. So if we do that, the 8.1 times 10 to the negative 3 divided by 0.5 liters, we get 0.0162. And then for our CH3COOH, we had 0.46 and half a liter. So that would be 0.23. Okay, so you have all your numbers. Let me just write this one in, 1.8 times 10 to the negative 5. Okay, so I want you to just solve this for H plus, just algebra, right? Multiply the bottom across, then divide what's remaining on the top. All right. This format of how to do this question, make sure you understand how we got our numbers, how we set it up. You're going to see this a lot in the next unit, acids and bases. Okay, what we did here really, right, this was acetic acid. We really set this up as our Ka. Okay, so this was our equilibrium constant for an acid. And in solving for that H plus will give us a lot of other information. Okay, so make sure you understand how to do this one here. All right. So our Le Chatelier stressors do not change the value of K unless it has to do with temperature. Okay, so be careful with that. If you change anything, your K is going to stay the same. It's always going to try to go back to reach K, except if we're changing the temperature. Okay, so the stressors change the concentrations proportionally. And that is the reason why our K does not change for concentration change. Okay, and so remember in last unit we had Hess's law where we can change the enthalpy values. We can play with the reactions and alter enthalpy values to find it for our goal reaction. We can do the same thing here with equilibrium. Okay, so we can have what we're looking for. We can have a bunch of smaller steps that each have their equilibrium constants, and from that we can figure out the Kc for our goal reaction. Okay, the changes are going to be a little different here though. So with these changes, if you multiply, so if we change the stoichiometry, that becomes an exponent. You're not multiplying the Kc anymore, it's an exponent. Okay, if you need to reverse the reaction, you do 1 over K. Okay, and then at the end, when we need to add things together, instead of adding, we're multiplying. Okay, so let's go through this one together. So if we have this goal reaction, our 2N2O plus 3O2 is in equilibrium with 2N2O4. Let's figure out how we're gonna make this. Okay, so N2O is only right here. Okay, so for this reaction, we need to flip it. And remember, if we flip it, we're gonna do 1 over our K value. All right, so that's for the first reaction. We have our N2O done. O2 is in multiple places, so let's skip that. Let's do our N2O4. We want 2 on the left side. Right now we only have 1. So I'm going to multiply that stoichiometrically by 2. Remember, if I multiply by 2, then I'm going to do this Kc value to the power of 2. I'm going to square it. All right, and then for O2, I need 3 of those on the left. Right now I have 1 on the right from the first reaction because we flipped it, and 1 on the left. Okay, so those cancel out right now, so we'll need to multiply this reaction by 4. So we have 3 on the left overall. And remember, if we multiply by 4, we do the power of 4. So 4.1 times 10 to the negative 9 to the 4th power. All right, so if we have our 3 reactions, let me do this in green. Okay, so our half of an N2 times 4 is 2 N2s. This one up here got flipped, so those two cancel out. Okay. For our O2s, we would have 4 O2 on the left, and we'd have 1 on the right. So this one cancels out. That changes to 3 O2 down here. Okay. Our NO2s, our NO2s aren't balanced, are they? Let me see. Okay, so we have 6 NO2s on the right side right now, and we want 0. So one of these reactions need to get flipped. Oh, this one, the N2O4 is on the right side. We should have flipped this as well. So that wouldn't be to the 2 power, it would be to the -2 power. Okay. So those 4 NO2s there and the 4 NO2s here would cancel out because that one get flipped. And we're left with what we need. Okay. So we're left with our 2 N2O because we flipped that. We had our 3 O2s left. And then we flipped the second reaction and multiplied by 2, so we have the 2 N2O4. All right. So that's the reason we make sure this matches at the end, because we can catch small mistakes like that. I just forgot to flip the middle reaction. All right. So since that matches, now we move on to our numbers. And remember, instead of adding here, we're going to multiply these. So we're going to do 1 over the 1.2 times 10 to the -35 times 4.6 times 10 to the -3 to the -2 power times 4.1 times 10 to the -9 to the 4th power. All right. And if we do the 3 of those, we should get 1.1 times 10 to the 6th. Okay. So our Kc for our overall reaction is equal to 1.1 times 10 to the 6th power. Okay. This example that we just did, this is probably the hardest example you'll see regarding this. Okay. There's a lot of steps here. Everything was changed. Normally it's not that extensive. But make sure we can do it at this level so that when we see one on a test or in our practice, it'll be easy, right? Okay. So that is what we're doing with essentially Hess's law, but for equilibrium constants. All right. So with thermodynamics, right, equilibrium connects to every unit. With thermodynamics, remember we talked about entropy. Entropy is the disorder or how spread out the energy is. If we're dissolving a solid, it increases the entropy, which means we have more product, right? So a greater K value also increases the entropy because that means we're product favored. That means we're dissolving more. So if you increase K, you're increasing the entropy. With Gibbs free energy, if you have K is greater than 1, remember we said that means it's product favored. If it's product favored, it's spontaneous. It'll move to the forward reaction. So we have a negative delta G there. If K is less than 1, it favors the reactants. So the forward reaction is non-spontaneous. Okay. Be careful with that wordage. We're saying the forward reaction for both of these. If we're talking about the reverse reaction, this would be opposite. Okay, but normally we talk about the forward reaction with these. Okay, so since there is a relationship there between K and G, delta G, we have an equation. This equation is on your formula sheet. Yes, it is on your formula sheet under the thermodynamics section, not under equilibrium. Okay, so be careful where you're looking. But you have an equation that relates delta G and K. All right, so moving on to our Rice tables. This section, I would say, is the most complicated part of equilibrium. This is the part that most students struggle with. Okay, make sure we understand our Rice tables because you will use this pretty extensively. This happens in this unit, it'll happen again in unit 8, okay? So with the rice tables, we use these if we don't know all of the concentrations, if we're trying to figure out the pieces of our question, okay? So what rice stands for is R is our reaction, okay? So our reaction is just the formulas, right? It's how it gives us a reaction. Initial is our initial numbers, so what we start with. Okay. The change, we normally denote that with x's, minus x's, and plus x's. That's just a change stoichiometrically, right? So if we have a coefficient of 1, we have just minus 1x. Coefficient of 2 is minus 2x. The products, we're making them, so it's a plus x. Okay, so that's what we do for changes. And then for equilibrium, those are our final concentrations after we reach equilibrium. That's also equal to our initial minus the change. Okay, so equilibrium is the I minus the change. Okay, so for this unit, we'll only be putting concentrations in the rice table. With acid and bases, there will be some moments where we can put moles in the rice table. But right now, that's not this. So we're only putting concentrations, okay? And we can solve for x after we reach the equilibrium, because remember we have our Kc as our product divided by reactants. We can put those into here, so C, A, and then B. So we can put those in there to solve for x, but you can see that this here, that algebra can get complicated, right? That's a quadratic. So to avoid quadratic, sometimes what we can do is called the x small approximation. Okay, so if you do the concentration you started with divided by 1,000, the concentration you started with divided by the equilibrium constant number, the number it gives you, and it's greater than 1,000, then you could ignore x. You just take x out of your equation, and that makes the math a lot simpler. Okay, so the concentration you start with divided by the equilibrium constant is greater than 1,000. You just ignore x. You assume it's small enough that it's not going to have a change on the concentration, a significant change. All right, so let's do an example with this one. All right, so we have this question here. We have after a 1.0 mole sample of HI gas is placed in an evacuated 1 liter container at 700 Kelvin, the reaction represented above occurs. The concentration of HI as a function of time is shown below. Okay, we're going to split this into 5 parts. We're going to find the Kc expression. We're going to determine what our initial HI concentration is and what it is at equilibrium. We are going to determine the equilibrium concentrations for H2 and our I2 using a rice table. We're going to sketch that concentration on our graphs, and then we'll calculate Kc. Okay, so taking this equilibrium process through the entire process and including a rice table. Okay, so starting with A and B, our Kc expression, let me do this a lot smaller. Kc is equal to, remember it's our products divided by reactants. So we have our H2, I2 for our products divided by the HI squared. Okay. Then it's asking us what is HI initially and what is it at equilibrium. So HI, I'm going to put an I on the bottom for initial, and then HI EQ for equilibrium. Okay, these numbers we can get from this graph that it gives us, because this graph is for HI. Okay, so the concentration of HI is a function of time shown below. So at time 0, we're at a concentration of 1.00. When it flattens out at equilibrium, that is the concentration we're looking for equilibrium, that's 0.80. So we have our initial and final concentration for HI. We have our Kc expression. So now the next part, so I'm going to move the screen down. We're going to need this information here. Okay, so make sure you have it written down. The next part is we're going to determine the concentration of H2 and I2. Okay, so for our rice table, remember reaction, the R is reaction, that's just the reaction as it is given to us. So we have 2HI, going to draw the arrows there because that's where they go. We have H2 plus I2. Okay, the I is our initial values. Okay, so we said our initial value for HI was 1.00. The initial value for our products, if the reaction hasn't happened, we don't have products. So our products are always going to be 0 at the start, initial. Okay, for our change is looking at if it's a reactant or if it's a product and what the coefficient is. So HI, we have a coefficient of 2. And it's a reactant, so we're going to subtract. So minus 2x. H2 is a product with a coefficient of 1, so plus x. I2 is a product, so we're adding, and a coefficient of 1, so plus x. Okay. And then the last part is the equilibrium. So our equilibrium, we actually know our concentration here, right? So we know this is going to be 1 minus 2x, because that's our initial minus concentration, or initial minus change. These are just going to be x and x. But we know this equals 0.80. Okay, so from this information here, we know that x is equal to 0.10 if we do that algebra, solve for x. Okay, so for this one, we didn't need to plug this back into the Kc expression. We didn't need to do the Kc or the x small approximation. We can just find x from algebra there because we know an initial and final value. Okay, so that means our H2 and I2, they both started as 0, but then they ended at 0.10 molar. Okay, so for part D, it's asking to sketch this on the graph. So we know for H2, our initial is at 0 because it's a product. Our equilibrium, we said, was 0.10 molar. Okay, so on our graph, we're going to start at 0. That's our initial. And our equilibrium should end at 0.10. Okay, notice how this graph here is not a straight line. It's curved. Okay, we're going to do the same thing. It's going to be curved, and it's going to reach an asymptote there at 0.10. All right, and then our last part, part E, is calculate Kc. So our Kc, remember we said this was our product, H2, I2, divided by the HI squared. We're just going to plug our numbers in. So our equilibrium concentration for H2 was 0.10, I2 was 0.10, and then for H2 we have 0.80, and this is squared. Okay, so for a Kc value, we should get 0.016 molar. Or sorry, not molar, just 0.016. Okay. All right, so moving on to another question. These ones here, we will look at our x to small approximation because we do have a K value there and we have an initial concentration. So if we do our initial concentration, am I right this way? Our initial divided by our Ka this time. If this is greater than or equal to 1,000, we can do x to small approximation. So if we do 1.51 divided by our 2.6 times 10 to the negative 5, that gives us, let me put this in, that gives us 58076. And that is greater than or equal to 1,000, right? So we can do an x is small approximation, okay? If you do an x is small approximation on an AP test, by the way, I would show this and write x is small so that whoever's grading it can know you're doing an x is small approximation. Okay, but let's go ahead and fill out our rice table. So we are looking for H plus. We have our starting is HC2H3O2. So we have our HC2H3O2. That's going to H plus. And then what's left is our C2H3O2 with a -1 charge because we got rid of that H. Okay. Our initials. We have our initial for the starting. We have that 1.51 molar. And remember, our initials for our products are always going to be 0. Okay. The change, it's a 1-to-1-to-1 ratio, so it's -x plus x plus x. So our equilibriums are going to be 1.51 minus x for HC2H3O2, and for products, it's x and x. Okay. But remember, we just did our x is mole approximation. That means for our reactants only, so only for the reactants, we can get rid of that x. Okay, so our Kc expression, or Ka here, Ka, which we said was 2.6 times 10 to the -5, is equal to our products, so our H plus times C2H3O2 minus, divided by our HC2H3O2. That's going to be equal to x times x divided by 1.51. Right? So to do the math here, you multiply the 1.51 over to the other side, and then you have x squared, so we're going to do our square root to both of those numbers. Okay, so that's just the algebra side of things. And when you do that, we should get our Ka is equal to 0.0063. All right, so that's how you do the x is small approximation. Remember, that's only getting rid of the x for your reactant side, not your product side. Okay, so our next topic we're going to talk about is our reaction quotient. Okay, reaction quotient is our Q. Don't get this mixed up with the equilibrium constant. Okay, so the reaction quotient is when it is not at equilibrium. So Kc, our equilibrium constant, is at equilibrium. This is what we want to reach. This is our end goal for the reaction. Qc is non-equilibrium. This is where we are right now. Okay, so it's going to be the same thing. It's still your products divided by reactants, the exact same equation. It just tells you a different thing. So Q is when you're not at equilibrium. K is when you are at equilibrium. Okay, so what Q means is, because it is not at equilibrium, if Q is greater than K, that means right now we have more products than we want at equilibrium. So to get rid of that extra products, we're going to shift to the reactants to get rid of them. If Q is equal to K, if it's equal to the equilibrium constant, then we're at equilibrium. So we're good, nothing changes, it's at equilibrium. If Q is less than K, that means we have more reactants than we want. So to get rid of those extra reactants, we shift to the products. Okay, so that's what Q means. It's the same thing as K, just not at equilibrium, so that we can know what we need to do to get to equilibrium. All right, so let's do a couple examples with this. So for the first one, we have a 6-liter vessel, has a mixture of 0.0222 moles of phosphorus trichloride, 0.0189 moles of phosphorus pentachloride, and 0.1044 moles of chlorine gas. Okay, we're doing two things here. We're calculating QC, and we're comparing it to Kc, okay, which our Kc is given there. So one thing here, make sure we remember our naming rules. We have a trichloride and a pentachloride. Okay, they're both phosphorus. Trichloride means it has 3 chlorines. Penta means it has 5. So be careful with that. Don't get those mixed up. But so let's go ahead and set up our Kc expression. So we have, let me zoom in so I can write smaller. We have our Kc is equal to PCl3 times Cl2 divided by our PCl5, right? Products divided by reactants. It's a 1-to-1-to-1 ratio, so no exponents. And let's plug things in. So our Kc is, or sorry, this is not our Kc. This is our current conditions. This is our QC. Okay, so that's going to be equal to, so our phosphorus trichloride, we said had 0.0222 moles. Okay, if we divide that by our 6 liters, moles divided by liters, we get 0.0037 molar. Our Cl2 we had right here, 0.1044. That divided by 6 gives us our 0.0174. And then our pentachloride was our 0.0189. That divided by 6 gives us 0.00315. Okay, so for our QC, we get 2.04 times 10 to the negative 2. Okay, so that's our QC. Now to compare to Kc, if we have, sorry, that should have been a negative 2, not a positive. We have 2.04 times 10 to the negative 2 for Q, 1.3 times 10 to the negative 4 for K. So our Q is greater than K. What does that mean? That means if our Q is greater than K, we have more product right now, so we need to shift to the reactants. Okay. So when it says compare to the K, comparing your Q and K, you want to mention the relationship, which one's greater than the other, and what it means. Don't leave off that what it means part. Okay. I want you all to figure out the second question. Okay. You should get a Q value equal to a Q value equal to 0.306. Okay, but show your work getting to that Q. Okay, these ones are in grams, so you'll have to go from grams to moles first, then do the moles divided by liters. Okay, but go from figure out your Q, write the expression out, put the numbers in to solve it, and then tell me what this means in relationship to your K value. All right, and then our last thing for equilibrium is our solubility product constant, right? So this is another K, KSP, right? I said we talk about this here in a minute when we showed all the different types in the beginning. KSP is still your equilibrium constant, but it's for solubility product. That's what the SP stands for. Okay, what solubility product talks about is the solubility in a solution, if it's able to dissolve more or less. Okay, so the higher your K value here, the more soluble it is. Because remember, if you're dissolving something, right, if we have NaCl, solid, that goes to Na aqueous plus Cl minus aqueous, right? If your K is greater than 1, the higher the K is, the more product you're going to make, so the more it's going to dissolve. That's what that's telling you, okay? But it won't be for NaCl. This will be for insoluble, not insoluble. It'll be for precipitates, okay? So anytime you have something that's a solid in a solution, so remember your solubility rules there, you'll have a solid and you'll have your AQ, your aqueous products. Remember, a solid does not go in your expression. So your expression, your Kc expression, is just your products when you have that solid. All right. So if you have a KSP and you find your Q value, like we just did, if Q is less than KSP, it will dissolve. Right? That means if Q is less than K, you're going more towards the products, so you're going to be dissolving your reactant. If Q is equal to K, it's at equilibrium, nothing's going to change, so that means you still have product in solution, or sorry, not product, you still have solid in solution, So you'll have a precipitate. You'll have that solid. If Q is greater than K, and that means right now we have more product than we need, we're going to go to the reactant side. And remember, the reactant is your solid. So if we go to the reactant, we're going to have that precipitate. We're going to make more solid. Okay. So this is the exact same thing we just did with our Q comparing to K. You're just going to have one term being a solid. That's the only difference. Okay. So I know this unit can be confusing, especially with the ice tables, and especially with Q and K being so similar but so different. Make sure we understand those terms. If we need help with this, make sure to ask questions. But that is the end of equilibrium. Our next unit is going to be acid and base. Have a good day.